Hello and thank you for clicking on our presentation. Our team name is the Power Rangers. We are a group of 5 final year mechanical and electrical engineering students. Today we will be presenting the design and development of the Feuerstrom wind turbine. So first, let's talk a little bit about what brings us here. The Renewable Energy Design Club at the University of Alberta has made the call for a design of a small-scale wind turbine to be implemented at the University of Alberta's North Campus. Renewable Energy Design, also known as RED, has specified that they would like the design to have the following 3 major characteristics. First, it should be efficient at low wind speeds, considering that the wind speeds on campus are much slower than typical wind farm locations. Second, they would like it to have a unique take on what a wind turbine should look like. It should attract viewers because of its creativity and aesthetics. And lastly, the wind turbine should be suitable for the use in front of the Donadeo Innovation Center for Engineering, also known as DICE building, which features a lot of the foot traffic, especially for engineering students and faculty. In response, the Power Rangers have developed a wind turbine called Feuerstrom. This is a 9-turbine system that meets RED's criteria and serves to symbolize the engineering students' passion for innovative engineering projects such as this one.
The specification matrix compares our achieved values with what was required of us to meet. As you can see, the column on the right is fully green, indicating that we met or surpassed the criteria required for the design. Note that the cost of turbine installation comes to about $1,515, which is $15 above the original budget set. Please note that this price is the total cost of 9 turbines and assumes over $100 in costs for 3D printing. However, since at least the majority of 3D printing is expected to be free by the use of the Elco Engineering Garage, this means that the effective price for 9 turbines will come to under $1,500. The following analysis summary will explain our cost analysis as well as the mechanical and electrical design analyses. The cost analysis will break down where exactly the budget will be going to. The mechanical analysis will explain how the blade was designed as well as how the entire mechanical system was put together. Finally, the electrical analysis will show how the wind energy will be converted to electrical energy that will be able to charge a 12-volt battery. This is a breakdown of our cost analysis. As you can see, the costs are quite evenly spread out, with electrical components taking up the smallest fraction. The entire list of materials comes out to about $1,500 as requested by RED. An additional option for the project is to add the cage, which will cost an additional $479.
To start our design process, our team considered the operating wind speeds of 1 to 10 meters per second and decided that a vertical axis wind turbine would perform better in lower wind speeds. From there, we came up with 4 different turbine blades and performed simulations for each of them. The simulations varied wind speeds flowing over a single blade while recording the torque produced. Our results show the 2-blade Savonius give the highest torque based on the graph, but ultimately a unique tapered Savonius blade was chosen because of its uniqueness and great performance. Following this decision, we completed a physical experiment with the 3D printed blade, which gave us rotational speeds at different wind speeds. The recorded rotations per minute and the motor efficiency were used to develop our efficiency curve. Here, our results show that our wind turbine is expected to produce 3 to 5.5 watts of power from a cut-in speed of 4 meters per second up to 10 meters per second wind speeds. Therefore, our wind turbine has a power rating of 5.5 watts, with peak performance estimated at around 9 meters per second. Finally, for noise level analysis, a time-dependent simulation was performed to find the sound power level of one blade at a worst-case scenario of 1500 RPM at 10 meters per second wind speed. The resulting simulation is shown on this slide, showing a maximum sound power level of 25 decibels. Hand calculations were performed to include 9 turbine blades and assess the sound pressure level at the distance of 1 meter and 6 meters away from the wind turbine. These values were found to be 23 and 8.5 decibels respectively. Therefore, the noise level analysis showed that our turbine will remain well under the noise limits set by the Alberta Utilities Commission.
For the motor, which is the heart of the turbine, we chose the NEMA 17 12-volt 350 mA stepper motor from Adafruit. This motor is capable of producing a substantial amount of voltage at low RPM and is able to charge our 12-volt battery at just 4 meters per second wind speeds. It is also inexpensive and easily accessible. The H-bridge voltage doubler is required to rectify the AC current from the stepper motor to DC current. This is because the battery only accepts DC current. It also doubles the output voltage of the motor, and so we were able to continue charging the battery at low wind speeds. The auto cutoff circuit is a safety feature we decided to provide as it stops current flow to the battery once the battery reaches full charge. This is so it avoids taking any overcharge damage. It also includes a 1 amp fuse for overcurrent safety and features LEDs that indicate the battery's charge completion. Wind speeds as low as 4 meters per second is enough to generate electricity to charge a 12-volt battery. With further field tests, it is possible to lower this number closer to 2 to 3 meters per second. Power Rangers developed an installation guide outlining the entire installation process step by step. Here are a few pages from our installation guide. It includes everything from 3D printing the blade to putting together the gearbox to pouring the concrete. The entire design can be built by University of Alberta students, and Power Rangers has even selected experienced and certified students for processes such as welding.
This is a top view of how the project would look right before the concrete is poured. We are looking from the top down. The green outline represents a dugout hole in the ground in front of the dice building. You can see wooden forms arranged into an octagonal shape, so that they form the shape of the concrete, with screws to secure the wooden planks. On the inside you can see our underground PVC base, which starts at the red rectangle representing our load. The PVC pipes carry wiring underground from the load all the way to each generator. Each black dot on the PVC structure represents a connection to one of the steel pipes supporting the turbines and generators. The steel pipes would be vertical in real life, so in this image they are coming out of the page. Our maintenance guide has simple instructions to follow to make the wind turbine last as long as possible. Some important points from our maintenance guide is that blade integrity should be checked every 3 to 6 months. Broken and or water-soaked blades should be replaced. Electrical components are not intended to be replaced. However, in the event that they are, careful care should be taken to ensure that the wires do not pull out of the PVC tubing. If any rust happens over time, be sure to sand it off and repaint. The overall assembly should be repainted every 3 years, or whatever the recommendation is on the paint used. Power Rangers has provided 2 recommendations for future work on the turbine design. The first consideration is wind tunnel testing. Because of the current pandemic, Power Rangers did not have access to a wind tunnel for proper testing. Instead, this was substituted by a different experimental test, which unintentionally introduced a lot of drag to the system. By using a wind tunnel, the drag could be eliminated from the test, thus giving a truer result. The second consideration is the addition of a braking system to the design. Most wind turbines experience much higher wind speeds, and as a result, need to engineer automated braking systems to avoid overloading their generator. Although it's not expected that the Feuerstrom will experience really high wind speeds, it is recommended that a braking system be investigated and possibly added to the design. Thank you, Red, for the opportunity to work on this project. Please feel free to send us any questions you may have. We look forward to hearing from you.